Okay, let's begin. So today we're going to talk about intersection forms and four manifolds. Um, and to get started, we're going to define intersection form in two different ways. The first way is using the cup product on cohomology. So just as a reminder, if you're giving two elements, two cochains, this is phi and c here, you can cup them together to get an element that's a cochain, the four cochain complex. And this is defined by doing this sort of action right here. It's not that important. What's important is that this induces a well-defined map on homology, on cohomology. And because we're talking about a closed manifold here, we know that the fourth homology of our closed manifold is generated by the fundamental class. And this allows us to define our intersection form. So we now can define the intersection form of a four manifold, a closed four manifold in this case, just to be the map from the product of the map from two cohomology classes to Z, defined by evaluating the cup product on the fundamental class. So this is the cohomological way. That's also a more homological way to think about it. This uses the intersection of surfaces in L. For this, though, we got to do a little bit of work first. And to start, we're going to prove this lemma, which says, if you give me a homology class alpha, then this can also be represented by a smoothly embedded closed surface. So let's see why is this the case. So first, we're going to take an element in the second cohomology, which is just the Poincare dual of, we're going to choose it so the Poincare dual is alpha, right? And then we note that if I look at the second cohomology of M, and I'm going to emphasize the group here, then this is similar to a proof we did last week with the temporal surfaces. Because we're going to say that this is, can be identified with a set of homotopy classes of maps from M to KZ2. And then KZ2, it turns out, is the same as CP infinity. And since the dimension of our manifold is 4, we know that this is actually the same as looking at homotopy classes maps from M to CP2. So the long story short is that if you give me a cohomology class A, I get some homotopy classes of some map, let's say F of A, from a manifold to CP2. And then we say, well, we know that CP2 has second cohomology, has second cohomology of the integers, which is generated by the dual of the CP1 sitting in CP2, right? if you think about how to build a CW complex for CP2, you get CP1 sitting in CP2 that generates cyclical homology. So this implies that A is just going to be the pullback of this class. CP1. Bracket. All right. So now, you know, we can say that, oh, we can always choose for this map FA to be transverse to the CP1. And when that's the case, we can find our surface F alpha just to be the inverse image of the CP1. And what this means is that the homology class represented by F alpha, so this F alpha, we know is going to be a closed orientable surface, smoothly embedded in our manifold. That's important. And we know that this F alpha is, well, there's an issue. It may be opposite orientation, right? May have issue with sign here. But the point is basically going to be the dual of A that a dual of A, which means it has to be the same homology class up to sign of alpha. And of course, if it's minus, we just choose the opposite orientation on F alpha, and we're fine. So that completes the proof. All right. So let's say we're given two homology classes. So we know now that they are represented by some smoothly embedded closed surfaces. So we call these F alpha and F beta. Then we can assume that these are transverse. And you know, the long story short is that since 2 plus 2 is 4, we know that the intersection of these two guys is just a signed number of points, right? Or a number of signed points. Yeah, that's fine. Yeah, this should go before here, and this should go after that. Okay. Number of signed points. The point is that if I give in two homology classes, alpha and beta, I can find the intersection between the alpha and beta just to be the intersection, the algebraic intersection number of these two surfaces. So here's an example. Let's say I have two framed knots. And I'm connecting I connect two handles to a surface like this. Connect two handles to a zero handle, and it has some framings. And we know we can that these have now cipher surfaces, and we can get actual closed surface by pushing the cipher surface into the four ball sum and capping off with the core of the two handle. And that's what we're going to define to be F1 and F2. All right. So what is the intersection number between F1 and F2? So I'm not going to go into detail about what's going on here, but just to give you an idea of how the picture looks. So in the two handles, the picture is simple, right? The two handles aren't intersecting, so we have like K1 being capped off and K2 being capped off. So there's no intersections going to happen in the two handles. But as we push into the zero handle, what we can do is create like a little movie. And the movie sort of goes like this. And don't worry about too much about why I know this is what the movie should be. All right. We can sort of isotope as we go down into the zero handle until these start touching. And if we do, we can attach them together. And we get a picture that looks like this. This is the picture we get. And this means that we can then isotope as we push further down into the zero handle. Here the picture looks like, I should keep this color coded. Let's make this from blue so you can remember which one is which. Like this. And so this is what we're going to do. We're going to similarly do another sort of like twisting isotopy on top. Where it make this look like, I think it's going to look like this, right? And kind of glue those together. And the long story short is we're going to get these two things that's unknotted. And these two guys like this, all right? All right, so now we can close up these surfaces. This unknotted guy, we can sort of just cap off as we go to the bottom. That's the wrong color. But when we try to cap off the black and the blue curve, what's going to happen as they get smaller is eventually they have to like cross each other. You know. And then after they cross each other, we can just cap off and there's not going to be any more intersection points. And the point is, literally the point is that this right here is going to be the intersection point. So that's sort of the way we think about, sort of picture how these things, these intersection points come about. So does that make sense?
Is there like a general way to like see the movie of like just a single knot going in?
So like if you give me a knot, how do I know what the movie should look like?
Yeah.
Yeah, but there's a process you can do to, it essentially comes down to just unknotting it, right? And that's what we call things called band moves that you can use to unknot the surface. You can see how the movie should look like. And that's basically what I did here is a couple of band moves.
Okay, thanks.
So, just going to state this lemma, which...
does the capping off ever intersect when you capped off the two handle?
No, because if you think about how two handles are glued on, the two handles are completely disjoint.
Okay.
Right. So you can't never have intersections inside the two handles.
Got it. Thanks.
All right. So here's the lemma that we all hope is true, is that these two definitions of intersection form, I should say, are going to be the same. All right. So what's the motivation for studying these forms? Well, part of the motivation is this theorem. Is that for any finitely presented group, there's always a smooth, closed, orientable Fourier manifold M, such that pi 1 of M is that group. And what that means is that there's a whole lot of Fourier manifolds, and we really can't really hope to ever really classify them. And so we focus on the simpler problem, hopefully, of how do we classify the simply connected Fourier manifolds? So we're going to like to assume that M is simply connected for pretty much the most of the rest of the, really of this course. And then when M is simply connected, we know that all the homological information outside of the second homology or second cohomology are all determined now, right? We know the first homology is trivial, so the third homology is trivial by Poincare duality, so forth and so on. So all of the homological information now is really contained in just the second homology or cohomology. And so these intersection forms really should tell us a whole lot of information about what's going on in these manifolds. That's sort of the idea, these simply connected manifolds. So that's like a little motivation for why we're doing all of this anyway. All right. So next we have the following lemma. So when M is simply connected, we know that the homology and cohomology, second homology, second cohomology, I should say, are torsion-free. And it really comes from using universal coefficients theorem here, because this guy is 0 and this guy is torsion-free, right? And of course, H lower 2 is isomorphic to H upper 2, right? So that's really why that's true. Also, so what this means is that this intersection form is really just an integral form on a free abelian group, right? And since M is closed, we also know that the intersection form is going to be unimodular, which means that the determinant of the intersection form is either plus or minus 1. And so the study of integral unimodular forms on free abelian groups is very vast. It's something that we know a lot about. And so let's talk about a few of the things we know about just these unimodular forms. So now we can, if we just leave the context of manifolds for now, what a unimodular form is just a, it's just a form on defined on a free abelian group, right? So it's mapped from L across L to Z. And we said that two forms are isomorphic, of course, if when we perform an isomorphism on L to get this new L prime, we get some commuting diagram like the one below, right? So doing the form in L with Q should be the same as doing the form with L prime and with Q prime in this picture. So next, we're going to define a few invariants for unimodular forms. The first invariant is pretty simple. That's just the rank, right? The rank of L is an invariant. It's pretty straightforward. The next invariant is what we call signature. This is a little bit larger. So if we consider the form L tends to R, which is just going to be a real vector space, then under some basis, we know we can diagonalize this form. And this form is just going to, it's gonna look like, this whole thing is just saying it looks like, lambda 1, yada yada lambda n, and then 0 is everything everywhere else. And we're gonna say that the signature of this form is just the difference between the number of positive lambdas and the number of negative lambdas. Also, if the, let's scroll this to the top. If the signature is either plus or minus the rank, then we say that the form is positive or negative definite. And otherwise, we say that the form is indefinite. And the last invariant we're going to talk about is called type. And so we say that a form is even if whenever you pair any element with itself, every self pairing gives you an even number, right? So it's so it's equivalent to 0 mod 2. And it's just called odd if it's not even. So here are a few properties that we just know about unimodular forms. The first thing that we know is that when the form is odd and indefinite, then we know that the form is isomorphic to just, ones and minus ones. It's isomorphic to just forms look like this. A bunch of ones, a bunch of minus ones. When the form is even, then we know that the signature is always 0 mod 8. And lastly, we know that if we know that the form is even and is negative definite, we have this formula to tell you exactly what the form should be. So it's always some number A times, I haven't told you what E8 was. I'll tell you what E8 is later. A times these forms E8 and H. I'll come back to this later. And what I mean by this is it's going to be and what this means is some number of copies of E8s and then some number of copies of H's. in this black matrix form. All right. And here, H is, I can tell you now, H is this guy right here. That's what H is. And E8 is, do I have this on here somewhere? I should, let's see. E8 is this guy. There's E8. All right, let's go back to where we were. All right, so let's go to 4 manifolds, back to 4 manifolds. So now we can define the rank, signature, and type of a 4 manifold to be the, whatever the same thing is of the intersection form that it has. We can call it even, odd, positive, negative, definite, indefinite, whatever, if the form is, right? So now we can use these forms to actually get some real invariance of these 4 manifolds. So let's do some examples. We get S2 cross S2. In this case, H lower 2 of S2 cross S2, this is just Z direct sum Z. And we know that this is generated by S2 cross the point and some point cross S2, right? So these are 2 generators in homology. So the first thing to note is that if I want to find, let's call this SQ and let's call this SP. If I want to find the self-intersection number of SP and SP, well, if I just push the sphere by a little bit, right? This is basically the intersection between, say, P cross S2 and P plus, some epsilon, push it a little bit, cross S2. And this is going to be 0. And similarly, SQ has self-intersection 0. And if you look at the intersection between SP and SQ, this is precisely the point PQ. And so with some choice of orientation, we get that Q of S2 cross S2 is just going to be this guy, which we find this to be H from earlier, right? With the right choice of orientation, of course, yeah. So, the rank of Q, let's call it QM, the rank is 2. And this matrix is, well, this form is isomorphic to, if I look at it as a form over the reals, it's isomorphic to this form. You can do this by just doing just some row and call operations here. And this tells you that the signature of the form is 0. And also you get that it's even, right? It's not hard to see. If I just multiply this out, you should get 2AB. And this is always an even number. All right. Yeah. So any questions about this example? Let me see if I can put the whole example on the screen. So let's do another example. Let's do CP2. So H2 of CP2 is, of course, is Z again, like we said before, and it's generated by the CP1 inside. And what this means is the form of CP2. Well, this is just going to be the same as doing, say, +1. The form just +1, right? We only have one generator. The self intersection with itself is +1. I'll also note here that the form for CP2 with the opposite orientation, well, this guy is just going to be just a form -1. So next, let's think about how forms work over connexons. So we know that the homology splits like this. I should say the H2 of this guy is splits like this. And of course, if you take a class in the second homology of the first guy and a class in the second homology of the second guy, they are not going to intersect. And so we get that the form we get from connexon is just the direct sum of the forms of each manifold, right? So, you know, we just get QM up here and QN down there. Good idea. So in particular, what this means is that the form for some number of, this I should write this. If we take some number of CP2s and connect sum it with some number Q of CP2s with the opposite orientation, we get that Q of M is just going to be P1s, it's P of these guys, and Q minus 1s. Just Q of those guys. So let's notice what this tells us. For example, we now know that S2 cross S2, CP2 directs, CP2 connects some CP2 and CP2 connects some CP2 with opposite orientation. These all have the same homology. The homologies are identical. But you see that these invariants are different, right? S2 is even, S2 cross S2 is even, while the other two are odd. S2 cross S2 and CP2 cross CP2 with the opposite orientation. These are both our signature 0. The other has 2. So this actually can help us distinguish manifolds more than homology can. The last example I want to go through is this guy that we did before, which is called K8. I'm gonna erase the circle. Not K8, K3, which is defined to be a submanifold of CP3, defined as above. And this has formed E8, direct sum, E8, direct sum, E8. And here E8 is a, and we just want to make a note that E8 here is a negative definite and it's even. And by direct summing a lot of the guys that we had before, we can get forms with various different properties. In Sevilia's book, we don't go into it that much, but if you go into Gunther Stiffjets, he goes into a lot of different forms you can get just by using these building blocks that we are pointing out right here. I also want to note that I've seen E8 define technically that the matrix here can find more than one way. Sometimes they have positive signs on the diagonals. This one has negative. So that sometimes you might see a different notation for E8. They're equivalent. Well, not equivalent, but they're another word I'm looking for. Sometimes E8 is defined in a positive definite way instead of negative definite way. I mean, whether diagonals are positive instead of, never mind. But the diagonals are positive instead of negative. So I'm going to finish with a few important theorems. The first question is, what does the form, how much is the form really telling us about these manifolds? And the first result we have is from Whitehead, which says that if two superconnected form manifolds, if you have two superconnected form manifolds, then there's an orientation preserving homotopy equivalence between them, if and only if their intersection forms are isomorphic, right? So this literally just detects the homotopy classes of these superconnected form manifolds. The next result we have is due to Wall, which says that if you're giving two superconnected form manifolds, if the intersection forms are isomorphic, then we know that for some non-negative integer, they're almost diffeomorphic, but not necessarily quite. You might also have to connect some with some number of S2 cross S2s. So as I connect some with some number of F2 cross S2s, they become diffeomorphic. But we don't quite know that they are diffeomorphic. And here's an example. If we let M to be the K3 manifold that we defined above, and we connect some with CP2 bar, and let N be 3 copies of CP2, and we connect with 20 copies of CP2. I'm assuming this should be var. Then it turns out that these two guys have isomorphic intersection forms. However, we can use Donaldson's invariants to distinguish them. For example, if I look at the Donaldson invariant for M, we get this guy. And the Donaldson invariant for N vanishes. And here, this E here, oh yeah, and this is defined on second homology, by the way. Yeah, these X is in second homology. And this E here is the Poincare dual of the CP2. The point is they're not the same. And since they're not the same, we know that M and N are not diffeomorphic. So these are two manifolds that have the same intersection forms, or isomorphic intersection forms, I should say, but they're not diffeomorphic as smooth manifolds. All right. This last result here says that if M is a simply connected closed smooth orientable for a manifold with even intersection form, then we know that the signature is 0 mod 16. And this tells you that, for example, we can't have an intersection form of a manifold that's E8 direct sum H. And you just check directly that the signature of this guy is not going to be 16. So not every unimodular form can be represented by a four manifold that's simply connected and closed and all that stuff. And all right, to finish up, I'm going to finish up with these final 3 results. The first is by Freeman. So if we're given a unimodular, if we're given a unimodular symmetric bilinear form, which is even, then we know that there's exactly one simply connected topological form manifold. So that's only up to homeomorphism with that form. And if it's odd, you can have 2. And in the odd case, we know that at least one of them is not smooth. It's never smooth, or not smooth, I should say. So what's neat is that this result tells us that our 2 manifolds from above, M and N, we know that these 2 are homeomorphic. N and M are homeomorphic, but they're not diffeomorphic. And finally, we'll end with these two results. The first says that if intersection form is positive definite, then we know exactly what this form has to be, or for a manifold, I should say. Intersection form for a manifold is positive definite. Then we know that the form has to be just a bunch of ones on the diagonal. And if the intersection form is even, then we know that the there's a letter missing here. Then the rank has a lower bound by the signature. And according to this book, this is all we have about the intersection function for a manifold so far. And that's all I had prepared for today.